Welcome to the QFE. I'm Rob Engel, and we're virtual at NYU today. We're extremely happy to have with us Tuomas Tomunen, who's assistant professor at Boston College in the Department of Finance, and has recently finished his PhD at Columbia, where there is a hotbed of important work going on climate research, and I think he's an important contributor to this. He has some very interesting results, which I think you'll enjoy today. But before I turn the program over to him, let me just remind you or tell you that next week we have another QFE. It's also the same time on Monday. It's going to be presented by three scholars from the European Central Bank. It's called Climate Scenario Analysis for the European Financial System. And it's going to be presented by Spiros Alaposkoubis, Katerina Budnik, and Paul Hebert. And I think they're all going to be presenting. And so this is a chance to see the inside of how the ECB is planning to design its scenarios for the stress tests that are ongoing at this point in time in several different flavors at the ECB. So the talk today is called Pricing Physical Climate Risk, and we're very happy to have Tuomas Tomunen here to talk about it. So the floor is yours.
Thank you, Rob, and thank you so much for the invitation. So today's work is joined with Viral Acharya, Tim Johnson, and Suresh Sundaresan. And it's actually the first time we are presenting the work in a seminar like this, so I very much look forward to all your comments. So yes, in today's paper, we ask whether physical climate risk is priced, and we are going to bring you some evidence from regional variation in exposure to heat stress. One of the main reasons why we are also concerned about climate change is that it is expected to intensify many naturally occurring hazards. So for example, as global sea level is expected to increase as a consequence of seawater getting warmer, that puts physical properties and other assets close to seawater at risk of getting permanently destroyed. Warmer seawater also tends to intensify hurricane formation, which also tends to amplify any types of damages. Now, these type of disaster scenarios are very often quoted, especially in popular media. But one thing that I would argue is not necessarily appreciated enough is that these type of hazards actually constitute a relatively small part of total damages that climate change is projected to cause on US economy. These type of damages are notoriously hard to estimate, but here are a few from relatively recent science papers. And as you can see, compared to these two hazards that I just measured, damages that are directly related to extreme heat or heat waves, they are almost order of magnitude larger in terms of annual expected damages by the end of the century. And the reason for this is that whenever temperature gets very hot, many bad things tend to happen. So for example, during extremely hot days, energy consumption and demand is expected to increase, partially because of more need for cooling, which already constitutes around 10% of total energy use or electricity use in the US. But not only demand, also supply will be adversely impacted because power plants tend to be less efficient when ambient temperatures are high, and also transmission losses are high during hot weather. And because these type of effects are not only local, they're not only affecting part of the country, which is the case perhaps with some of these other hazards, they are affecting the whole country. When you aggregate this up, you actually get to a number that is significantly higher than what you typically see from these other type of hazards. But not only electricity, hot weather is also causing other adverse consequences. So for example, it decreases labor productivity, especially in industries where workers are directly exposed to extreme temperature, such as construction, manufacturing, mining, or agriculture. Now, in the emerging climate finance literature, one of the major questions is to what extent risks related to climate change are already affecting asset prices. And while there has been lots of good work being done in this area, I would argue that one relatively understudied area is to look at heat waves and heat stress, which again constitutes perhaps the biggest channel through which climate change affects US economy. And that's what we are going to look in our paper today. So just to give you a preview of our results, we are going to look at heat stress exposure for two different types of entities. We look at US municipalities and also US corporations. We have measures at entity level, how exposed they are to projected increase in heat wave related damages, and we estimate how exposure to this risk affects various asset pricing outcomes. So as a quick preview, we estimate that a municipality that is projected to lose 1% of GDP as a direct consequence of heat damage, the bonds that they have issued, credit spreads are approximately 15 basis points higher than for municipalities that don't face this risk at all. For equities, we find that one standard deviation increase in heat stress exposure increases conditional expected returns by 50 basis points. And while we do some horse race type of analysis at the end of the presentation, we don't find similar evidence for other hazards that we can measure, such as droughts and flooding, perhaps again suggesting that when you look at aggregate impact on climate risk, on physical climate risk on US economy, heat stress seems to be perhaps most important. Here is a graph that pretty much summarizes our main results. So in this graph, it shows our coefficient estimates year by year, both for muni bonds and also for equities. It estimates how one standard deviation increase in heat stress exposure is going to affect credit spreads on municipal bonds or expected returns on stocks. And you can see that during early part of our sample, we don't find too much evidence. But after 2013, 2014, you can see that gap between highly and low exposure entities starts to emerge, so that by the end of the sample, more exposed entities do have higher returns and also forward-looking expected returns and also higher credit spreads. So a figure like this is very much consistent with some of the arguments put forward in climate finance literature, which is that attention and concern towards climate change has increased quite significantly over the past decade. Now, there is lots of interesting work that has been done in the literature. I'm going to skip them in the interest of time and talk about how the rest of the presentation is going to be organized. So I will start by explaining how we are going to measure heat exposure, how we are going to construct our measures, and then I'm going to split the rest of the presentation in two. So first, I'm going to talk about our data, our empirical approach, and results for municipal bonds. And then I do the same thing for equities, again, talking first about the data and empirical approach, and then present the results, and then put these together and wrap things in the end. I see a comment from Sean asking if winters are getting warmer too, and are these benefits gonna offset damages from heat waves? The answer is yes. I'm gonna show our measures, but actually some of the municipalities, especially up north, are gonna benefit from this because there is gonna be less need for cool heating during cold months for these municipalities. But yes, there is an offset, but the average is definitely on the side of adverse impacts. The average municipality is definitely, based on our estimates, going to suffer more than they are going to benefit. Okay, so our first measure comes from a recent paper published in Science by Solomon, Zhang, and co-authors. This is relatively recent, but highly cited paper that tries to estimate at relatively high, fine geographical resolution what are the damages caused by climate change for US economy. So the unit of observation that they have is a county, which is kind of nice because that gives you lots of geographical variation. They have kind of like bottom-up approach. They estimate these damages for various different hazards, such as damages to agriculture, hurricanes, and even something like crime rates. But for bulk of our presentation, we are going to be focusing on direct consequences of extreme heat, which in this case are going to be related to increases in energy expenditures and decreases in labor productivity. But I'm going to talk about these other hazards towards the end of the talk. Just to give you an idea, what is the data we get from their analysis? One unit of observation we get, for example, says that by the end of the century, as a consequence of climate change, New York County is expected to, energy expenditures in or consumption in New York County is expected to increase by 9.2%. The labor productivity in highly exposed industries like construction is expected to decrease by 1%, and by 9 basis points in low-risk industries. Think of your office workers in Wall Street and others. So for them, the effect is relatively minor. Now, we could use these measures directly in our analysis, and the results would go through. But in order to get some economic magnitude for these quantities, and in order to combine them into one aggregate heat measure, we are going to convert them into absolute dollar damages in a relatively crude way. So we are going to take 2019 state level data on energy expenditures and use that as a measure for increased energy expenditures and how much it's going to cost in 2019 dollars, essentially assuming that energy supply is fully elastic and not the price is not going to respond to increase in demand. Also for labor productivity, we are going to quantify that by using lost wages, essentially using wages as a proxy for value added by labor. And we do this also by industry basis. Okay, I see a comment asking about what exposure means. Here we are talking about levels of exposure. So we are taking two entities and asking, for example, how much of their GDP they are expected to lose by the end of the century based on these measures as a direct consequence of excess heat. So yes, we are not estimating any type of betas with respect to some shock. We are directly getting a level measure from these sources that I'm going to cite. Will I be able to say anything about whether these premia reflect clientele effects, rise of ESG investing, or revision of beliefs about cost of climate change? No, this is something that I'm not able to say. I'm going to show that there seems to be an impact on asset prices, but whether this is through some belief channel or revision in damages or preferences or beliefs about climate change, I have relatively little to say. Question: why should expected return rise when expected damage increases? Basically, that's a very important point. We're going to look at forward-looking measures of conditional expected return. and yes, if risk increases, that should constitute a negative cash flow shock, meaning that the realized returns are actually lower. But after that, if there is a risk premium on climate risk going forward, if investors demand a premium for exposure to these type of risks, the expected return should then be higher. But I'm going to talk about this more towards the later part of my presentation. Okay, so that was our first measure. Our second one comes from a company called 427, that is essentially a subsidiary of Moody's. And what they attempt to do is the same thing for physical climate risk than that credit rating agencies do for credit risk. Essentially, they assess how exposed different entities like US municipalities and US companies are to various physical climate risks, and then they assign scores based on their exposure, where 0 means very low exposure and 100 means very high exposure. They do this for various hazards. Again, we are going to focus mostly on heat stress, but I'm going to talk about this other risk towards the end. Their approach is very similar to the science measure in the beginning, in that they assess how exposed different geographical regions are to different climate hazards, and then they assign scores to entities based on their physical location. For municipalities, this is relatively straightforward because we know where they are located. For companies, they use production plant or physical asset level data, essentially. Think of production plants or offices, their locations, and then they aggregate from there to create a company level measure. There are some important limitations with the second one. The first one, the obvious one, being that this is proprietary measure, so it's somewhat of a black box. Also, it's fully relative in a sense that we can say if one entity is more exposed than the other, but it doesn't give us any sense of dollar magnitudes. So for these reasons, I would argue our first measure is the preferred one when we look at municipal bonds. But for the corporations, the benefit of the second measure is that, well, it is available because the 427 has done this assessment globally, and they have locations of physical assets globally. So we are going to rely on this in the second part of our analysis. Here is one heat map used for its original purpose, which shows how exposed different municipalities in the US are to heat stress based on our science measure. And you can see that the most exposed municipalities, they are expected to lose something like 2% of their GDP annually as a direct consequence of heat. This scale here is truncated at 0. But as Sean suggested, some municipalities are actually going to benefit. The measure for them is negative, meaning that they are actually going to benefit to some extent due to the decreased frequency of very cold days. Here is the same measure for 427. Overall, these two measures agree to quite high degree. I think the rank correlation is something like 0.6. They do disagree a little bit in terms of where the most exposed area is located, but overall they otherwise agree very highly. I had a comment that why state boundaries are so sharply defined. That comes from the fact how we move from relative damages that the science measure gave us into actual economic damages. We use some state level data on things like energy prices and wages, which creates these type of sharp boundaries. Again, we could run the whole analysis using the original measure itself, which is more evenly distributed, and it wouldn't have this type of state boundaries, and the results would go through, but they would be a little bit more difficult to interpret in terms of their magnitude. So that's why we have moved to this type of absolute measures. Whereas the second one doesn't have any such state level inputs to the same degree. Okay, so here is the summary statistics for our risk measures in the sample of US municipalities. The first is the heat damage, which is our aggregated damage measure from the science paper, which again is simply the sum of its three components: energy expenditures, how much they are going to increase as a consequence of climate change, and economic value loss as consequence of decrease in labor productivity. And you can see that the average municipality is expected to lose something like 83% of GDP every year as a consequence of heat damage, a bulk of which comes through this energy expenditure channel, but labor productivity also contributing quite meaningfully. One thing I probably should mention is that one of the limitations of this type of bottom-up approach that we have is that our measure does not capture all channels through which heat waves can damage the economy. So for example, extreme heat tends to increase the depreciation rates of physical assets. Think of roads, bridges, or buildings. These type of damages are not captured by our measure. Similarly, extreme heat has adverse impact on human health, which arguably would increase healthcare costs. These channels are not captured by our measure. So I would argue that this 0.883 is probably an underestimate in terms of the magnitude of of the total damages. But that's an inherent limitation of any of this type of bottom-up approaches, that you have to make choices which channels you model. Okay, so now so these are our measures. Now let's move on to municipal bonds and what we do with this data. So on left, you see again the heat map that I showed you earlier. And one of the immediate concerns that might come to your mind is that different regions of US are differentially exposed to heat stress, but they are also different for many other reasons. Local economic conditions vary a lot across the country. So maybe maybe your measure is just picking up some of these other type of differences in local economic conditions that don't necessarily have to do anything with climate change. So how you're going to tackle a problem like that? Well, earlier literature that has mainly been focusing on sea level rise has tackled this challenge by looking at sharp discontinuities in risk exposure. So you could take one municipality or even something like one school district or one house that is very close to the sea border and thus very highly exposed to increase in sea level. And you would take a comparable observation that is just a little bit inland, economically very similar, except arguably for the fact that one of them is exposed to sea level risk and the other one is not. So then you can use the second observation to control for any local economic conditions. In our case, that's unfortunately not going to be possible because heat by its very nature wants to distribute itself as evenly as possible. I mean, it's one of the most fundamental laws of physics. So if I take two municipalities that are adjacent to each other, their exposure to extreme heat are going to be very close to each other without any sharp discontinuities. So just to quantify this, I think it's already pretty obvious if you compare these two figures. But if I would take adjacent municipalities and calculate the rank correlation of their heat scores and sea level scores, you can see that for sea level score, they are positively correlated, but only by something like 0.28. Whereas with heat risk, they are almost like 0.98% correlated. So again, there isn't like sharp discontinuities. The variable is very evenly distributed, with very relatively small gradients in terms of exposure. So then the question is, what are we going to do instead? Our approach builds on the following observation, which is that historically credit rating models haven't explicitly reflected climate risks. So here is one quote from a 2015 white paper by Moody's, where they discuss how environmental risks affect their credit rating assessments. And they actually explicitly state that because climate change is expected to materialize over a relatively long time period and its impacts on the economy are very much uncertain, direct climate change hazards are not at present material driver for ratings. So we actually went through these credit rating manuals where the three agencies describe their methods for local US governments. And 2019 was pretty much the first year when these documents and manuals actually started to explicitly talk about climate change risk. And this is changing very rapidly. All of these agencies are currently investing heavily in their capabilities of assessing physical climate risks. They have white papers out as we speak, where they talk about how they are going to revise their methodology related to physical climate risk. But I want to emphasize that this is all very recent development that has occurred only very recently. But we didn't want to rely only on this type of narrative approach. We did some analysis ourselves. So what we did is that we took all the prospectuses of newly issued municipal bonds since 2010, and we calculated what fraction of them mention climate change in the whole document even once. So if you take a recent prospectus that talks about climate change, it typically is located in the material risks section and how climate-related risk might affect the creditworthiness of the issuer. But we kind of wanted to give this measure a benefit of doubt and kind of assume that if climate risk is mentioned even once anywhere in the document, it's something that is being discussed. So what you can see is that early part of our sample, the climate risk was discussed very little. Something like 3% of prospectuses mentioned it even once somewhere in the document. This has been changing recently, and in 2020, almost like 15% of them already talk about climate risks. And if I would extrapolate from here to the future, I would. It seems to me that going forward, climate risk is going to be more and more discussed as an important component of credit risk. But as little back as 2017, only approximately 5% of the prospectuses talk about this. So again, this evidence very much consistent with the narrative that I mentioned earlier, which is that explicitly accounting for climate risk has been very recent development. Now, what does this mean? Well, if credit ratings had always taken climate risk perfectly into account, and I would try to use credit ratings as a control for other type of credit risks that might affect municipal bond spreads, that would be kind of like throwing baby out with the bathwater, because that would drive away all the variation in my variable of interest, which is the heat risk. But if it's really the case that credit ratings didn't reflect this type of risks, I can actually use very flexible credit rating category times year fixed effects to control for any traditional sources of credit risk that have a first order impact on credit ratings. Think of, for example, municipalities' leverage ratios as a fraction of their tax revenue, or things like pension obligations or other important things. Now, with this approach, our identifying assumption essentially becomes that in addition to climate risks, there are no other omitted risk factors from credit rating models that would have a first order impact on spreads that would be positively correlated with heat stress in the cross section. Now, our data comes from very standard sources. We get characteristics and ratings from Mergent Municipal Bond Database and secondary market prices from MSRB. Our sample selection follows very much the municipal bond literature, with perhaps the one important point to mention is that we are not going to use any bonds issued by states themselves. We are going to focusing only on entities that are more local level because our risk measures are more granular. So any state issued bonds are not going to be part of our sample. Here is the summary statistics for our muni bond sample. It's going to be a panel, bond month panel from 2006 to 2020. A typical bond in our sample has a credit spread of approximately 70 basis points and time to maturity of 12 years and so on. Our empirical specification, it kind of has like a diff and diff type of flavor in it, in a way that we are going to estimate, instead of doing just pre and post, we are going to estimate year by year how much 1 unit of heat risk exposure is going to affect municipal bond spreads in that year. So this coefficient of estimates here are these alpha y's that you can see here. This type of specification allows us to control for many things. Most importantly, we're going to add credit rating category times year fixed effects to our analysis to control for any unobserved variation in important quantities that affect the issuer's credit worthiness. So here are the results. These are pretty much the same results I showed earlier in the figure, but now they are in table format. The first two columns are measured with our science heat damage measure, and the two last columns are using the 427 heat score measure. And if you compare, for example, the first and the second column, they are otherwise the same, but the first one does not include these credit rating fixed effects, whereas the second one does. The same thing for third and fourth column. The first one is without, and the fourth one is with credit rating fixed effects. And the first thing you can see that including them actually does relatively little to our estimates, suggesting that indeed it doesn't drive away variation because the models themselves did not necessarily account for climate risk, at least historically. And the way you read this is that compared to 2006 baseline year, in the early part of our sample, there wasn't exposure to heat stress, didn't have a significant impact on credit spreads, but towards the later part of our sample, gap starts to emerge. So that, for example, in 2019, the point estimate is that if municipalities expected to suffer damages each year that equal to 1% of GDP, their credit spreads are 17 basis points higher, excuse me. With the 427 measure, you can read this, the magnitude as 1 standard deviation increase in heat stress exposure is going to increase spreads by 7 basis points. Now, after looking at the full sample, we could also look at some of the subsamples. We find that the results mainly come from long-term bonds, those that are more than 10 years, have more than 10 years time to maturity, kind of suggestive that climate risks are not necessarily gonna materialize over the next few years, but over the following decades and even longer time periods. Results mainly come from bonds with lower credit ratings. I mean, if you're very highly rated, and even if your cash flows are adversely impacted by heat damages, you're not necessarily going to default. But if you are already more distressed, that might push you over the boundary. Also, we find that the result mainly comes from revenue bonds instead of general application bonds. In addition to this type of subsamples, we can actually zoom in a little bit more into the mechanism. What we can do is that we can decompose our science measure back to its 3 original components, which were energy expenditures and high and low risk labor. And when we do this, we actually find that most of our results come from energy consumption and high risk labor. You can see that both of these results are very similar to the full sample results. The low risk labor, the table has lots of stars in it, but that's essentially just reflects a base year effect. So the fact that essentially everything is significant means that nothing is significant. If I would rebase my analysis to basically any other base year, the result would essentially go away. So this is not robust to change in base year. So for example, we cannot say that 2019 would be significantly different than even 2008. So the evidence for energy and high risk labor are where our main result seems to be coming from. Okay, so that was our evidence from municipal bonds. Now let's move on to equities. So whenever you run an analysis where your y variable, is credit spread, and you find that the exposure to heat stress or some other type of risk increases credit spread, you cannot really distinguish whether that is due to adverse impact in expected cash flows, meaning increase in expected losses, and or if there is some risk premium attached to this thing. Before I go there, there is question about 2009, where our coefficient estimates in some specifications is surprisingly high. Let me actually, that is a little bit of an artifact, but there is actually also one potential explanation that is consistent with our climate story. So if you look at historically how much people have Googled climate change and look at Google Trends, how has it changed over time, it is increasing after 2013 or 2014. So very much consistent at the same time period when our estimate starts to become significant. But there was actually already peak in 2009 due to the Copenhagen Climate Summit. So you could, like, I don't want to go all the way there because that would be, you know, pushing our interpretation too far if I would claim that this is conclusive evidence. But at least it's consistent. It's consistent with the notion that it is possible that 2009 was a little bit special year in our early sample, in the sense that that was the year when attention to climate risk was much higher than in other years. So that's one potential explanation for that one observation. But yes, let me go back to equities. So yes, when you have credit spreads, you don't know if there is increase in quantity of risk, if you will, or increase in expected loss, or if there is risk premium attached to that risk. And to make progress, we are actually going to look into equities. Now, one challenge is that when you want to look at expected returns, they are notoriously hard to estimate from historical sample, even in unconditional sense. But that's not actually even going to be sufficient for us, because we need a conditional estimate for expected returns, because as our earlier evidence suggested, climate risk has seemed to have been changing over time. So any unconditional estimate actually won't do it for our purpose. But there has been recent developments in terms of creating measures for conditional expected returns. Martin 2017 and follow-up paper by Martin Wagner 2019 proposed that you can actually create measures for conditional and forward-looking expected returns by using options data. So essentially their measures of expected return is related to the risk-neutral variance of the underlying asset. These are relatively new measures, but have already been adopted by some researchers. What kind of convinced me that these type of measures are able to pick up something related to expected return was their table 6, where they show that if you would put rank stocks into portfolios based on their conditional expected return measure, and then compare the average of their conditional measure at portfolio level to the average historical returns, you can see that the measure actually captures very nicely variation in average returns. regardless of how fine of a split you do for in your portfolio. So this was kind of like evidence that to me suggested that their measure might be very useful for our purpose as well. So our data come from standard sources. Option prices as characteristics come from option metrics. Stock price and balance sheet items come from CRISP Compustat. Our sample is going to be S&P 500 because single name options are mostly available for those entities. Also, our risk scores are mainly available for S&P 500 companies. The specification we run with equities is very similar to the one we use for municipal bonds. And here are the results. So again, in this case, our Y variable is our measure for conditional forward-looking expected return. And we find that early part of our sample increase in heat exposure does not really affect our measure, but starting 2013, 2014, a positive spread starts to emerge, which is actually, to me, it's astonishingly similar to the result we find with municipal bonds in terms of the timing and also in terms of the magnitude. So again, these results suggest that towards the end of our sample, exposure to heat stress results in higher expected return, meaning that there is a positive risk premium for exposure to heat stress. Now, what does this mean? Well, to me, this result is actually very interesting because if you take two assets, one of them is exposed to climate risk or any other type of potential loss compared to otherwise equivalent asset that is not exposed to this loss, the first asset should unambiguously have lower price simply because its expected cash flow is lower. But what's not unambiguous is what is the sign of premium for that risk, or whether there is premium in the first place. Because there is actually different classes of macroeconomic models of climate change that makes different predictions on the sign of the risk premium. You can construct a model where climate change materializes as an consequence of high economic output, in which case, whenever economy is doing well, that's the state of the world when there is lots of pollution and climate change is bad, which means that the climate risk actually acts as a hedge against against aggregate output, in which case your risk premium on climate risk would be actually negative. But on the other hand, you can also construct models where climate risk itself damages the aggregate economy, meaning that in those states of the world where climate change is bad, also aggregate output is low. Think of like Barrow rare disaster type of model, for example. And in these type of models, the premium on climate risk is going to be positive. And our result in the previous slide is actually consistent with the second view of the world, meaning that our results suggest that climate change itself seems to be damaging enough that there is a positive risk premium attached to physical climate risk. Before I conclude, let me do a little bit of a horse race with some other risk measures. Again, I mentioned earlier that we can measure other type of hazards, not only heat risk, but also things like drought, excess rainfall, hurricanes, and sea level risk, and see if I would repeat the analysis for these other risks, how would they compare to our heat risk measure. There is one important caveat here. I don't think this horse race is perfectly fair in a sense that because we measure our risk exposure at municipality level, if there is any within municipality variation in risk exposure, which is definitely the case for things like sea level risk and even to some extent hurricane risk, we have an errors in variable problem there, which biases our results towards zero. So for this type of risk where you have very big exposure gradient, our approach is not going to be very fair for them, if you will. But that caveat in mind, when we do this analysis for all these different types of risk, droughts, rainfall, hurricane, and sea level, we find that heat risk is the one that turns out to be significant, both in the municipal bond sample that you see here, but also in the sample for companies. Although for flood risk, there seems to be some action going on here in the middle. Great. So now let me just provide you with some concluding remarks. So our results suggest that exposure to physical climate risk and its arguably most important component, which is heat stress, seems to be a systematically priced source of risk across different asset classes. And the fact that we find positive premium suggests that climate change itself, markets might think that climate change itself has a negative impact on aggregate economy. And this actually, as Geekley and co-authors discuss in their recent paper, this has very important consequences for any climate abatement investments, because if risk premium for climate risk is positive, it means that discount rates that you should apply to any climate abatement investments are actually lower, which means that any investments that are there to prevent climate change from happening actually are more NPV positive under this type of view of the world. The second, I would say a concluding remark is that it is important when you think about how to measure exposure to physical climate risk, it's important to make a clear distinction between different types of hazards. So our results suggest that heat stress is the source of risk among physical climate risk that seems to be most consistently affecting asset prices, perhaps due to its large magnitude. And to me, this is very helpful observation for any type of policy debate about physical climate risk disclosure. So SEC, Fed, European Central Bank, and others are currently revising their rules about physical climate risk disclosure requirements, and our results kind of suggest that because heat risk seems to be such an important component of physical risk, it should be definitely reflected in a clear way in any disclosures about physical climate risk as a whole. But for now, I would like to thank you all for your time and excellent questions, and I would be very happy to answer any further questions that you might have.
Well, thank you very much, Tuomas. It was very interesting. You cover a lot of ground that's been people have been trying to figure out how to do this, and you've given us some suggestions. You didn't say anything. I have a quick question. You didn't really say how you define high-risk labor and low-risk labor, and what the impacts, why the labor productivity was different for those two. Is that, I mean, somebody else classifies them, or how did you do that?
Yes, that's a fair point. Sorry if I went through it too fast. So yes, this classification and distinction comes purely from the industry that we are talking about. It comes from the science paper itself. So industries such as construction, manufacturing, agriculture, and mining are classified as high-risk industries due to their workers' direct exposure to outside heat, whereas any other industry, service workers are typically, and those industries are typically considered low-risk industries because they tend to work in more climate-controlled environments, if you will.
And is this reported by the industry themselves, or did the people in science just kind of introspect?
My understanding is I don't think this is reported by firms or industries themselves. I think they base their classification on earlier research about exposures of different industries. It's a relatively coarse distinction, of course, because different firms do have different exposures based on their unique considerations. But overall, there has been research about like aggregate level differences in terms of workers' exposure based on what type of occupation they are in.
Tuomas, I have a couple of questions.
Yes.
One is chart or slide 12. You show the comparison of heat and sea level risk.
Yes, here.
And I'm just wondering if you could isolate this to the Florida region. What would the combination of those two things look like? And is there an interplay between those two kinds of physical risks? That's the first question.
There could be. Florida is definitely a region that is exposed to many different hazards at the same time. Like two metropolitan areas in Florida, which are Tampa Bay area and Miami area, are, in addition to New Orleans, the three most exposed areas to sea level rise.
Right.
Florida is also one of the most exposed areas for hurricanes in the whole US. And also, if you look at our heat map, Southern Florida especially are also very exposed to heat risks. So they seem to be exposed to many things at the same time. Whether there is some interplay, I would say there should be. Like ultimately, what investors should care about is the total amount of damage that different channels cause to that particular municipality. And in case of Florida, that damage seems to be coming from many different channels. We are not really able to quantify that type of interplay. However, simply because it's relatively. We still have relatively few observations, and trying to do some type of interactions would probably be pretty difficult. One thing I do want to mention is that, when we do this horse race, we just put all the variables in the same regression, and it does seem to be that heat is the one that is picking most of the action, not the others. But it doesn't mean that there is no action in this other risk. It's just that we don't have enough statistical power to pick it up.
And my second question is, when you think of just about heat, and you look at just high risk and low risk labor, your low risk labor would include people who work presumably in offices and maybe hospitals and other indoor locations. Now, suppose that we have a heat shock in a particular part of the country that's particularly vulnerable to it, and it creates brownouts in that region because of the heavy demand for air conditioning and so on that they're not capable of meeting. Does your analysis allow for sort of capturing the spillovers from those kinds of things, like hospitals who can't function without the electric power, even if they have generators and other related things?
Mm-hmm. Not directly. I would say to some extent our energy demand measure should be capturing those type of effects, but in terms of like brownouts and other things, not directly. And as I mentioned earlier, like that, to me, that's one of the limitations of our measure, is that there are many other ways through which hot temperature affects economic outcomes in our society. And right. those type of things should just amplify the magnitudes that we are observing here, making the damages larger.
Hugh McCullough has a question. Do you want to ask it, or should I read it?
Yes. Is the 0.83 annual loss in GDP loss from 1 degree Celsius warming, or one-time loss from one-time warming? It's a loss between two scenarios. So there is it's a loss compared to state of the world where climate change reaches its business as usual scenario, RCP 8.5, compared to a counterfactual where climate change did not occur at all. And this damage is something that then occurs each year compared to a scenario where climate change did not occur. So it's not one time, it's not 1 degree, it's the total damage each year that climate change as a phenomenon causes compared to counterfactual where it didn't occur at all. I hope that that answers the question.
Are there other questions? Well, I had one, which it sounds like Viral has already answered, but basically, when you know something about the variance of the stock, whether it's from the options market or any other sort of measure, it takes something else to tell you something about the expected return on that stock. I mean, it's idiosyncratic variance presumably is not priced at all. Systematic variance is priced. So I'm not sure what the argument is. I mean, I guessed that it was maybe Steve Ross's argument about the options prices have some information about the mean in there. I don't know whether there are other ways to learn about the mean from the variance of the stock.
Yes, that's a very fair point, and it's definitely like we are relying very heavily on Martin Wagner interpretation of their measure as telling us something about the mean. One thing is that we are not measuring expected return as a risk neutral variance itself. It's a measure that takes into it not only the risk neutral variance of the company itself, but also average risk neutral variance of all companies and their difference. And they argue that that should tell you something about the mean. And as I mentioned, at least based on their evidence, and if you look at this unconditionally, their measure does seem to at least predict average returns over a long time period. So in that sense, at least unconditionally, it does seem to be telling you something about the mean as well.
Does it tell you that when the variance changes, that the mean changes too? In which direction?
It should tell you that. So if everything else is constant, but one company, its measure of risk neutral variance increases, that would suggest based on their measure that also the mean should increase, and the average the expected return itself should be
So
higher.
I mean, that plot, you said it was the average return. So if it is it the average return when compared with the average risk neutral variance? Is that, or is it the risk neutral variance at a point in time and then the average return something after that?
Yes, so their measure itself is something you can compute in any point of time. So that's, you know, day by day or month by month basis, because you can compute the risk neutral variance. But then how do you argue that? How do you argue that that is then related to average returns? Well, day by day conditionally basis you can. That's pretty much untestable because you have one observation in realized returns. But then if you would now aggregate over time and see if your measure at least on average hits the mark, then when you reach graph like this, which says that on average at least over a long sample period, you seem to be your measure seems to be capturing variation in returns.
Okay. I don't think I'm convinced, but that's all right.
Okay.
Other questions? Well, we've actually used our time up, so let us thank you again for an interesting talk and on a tough problem. So it's good to see progress. And do tune in again next week for the ECB presentation on stress testing for the European banks. So thanks very much.
Thank you so much.